The steps in multiple linear regression are basically the same as they are for simple linear regression, but we have some things to be on the lookout for. And the two primary things are overfitting, which we'll discuss in detail next week when we look at error metrics, and multicollinearity, which we will discuss now. With multiple predictors, it is possible for predictors not only to be correlated with the response, but also to each other, and that can make things difficult to interpret. So we are going to introduce an option in our regression analysis called VIF, which stands for Variance Inflation Factor. And we will examine these values of VIF. And for any variables where VIF is greater than 5, we will start eliminating them one at a time, starting with the biggest one. And this threshold of 5 is largely accepted, but it is somewhat arbitrary. Depending on your data and your goal in your analysis, you could tweak that value. We'll stick for 5 for now. And after we run MultliReg and find our remaining variables, we will discuss programmatically how to write our equation and use it to find a prediction. In today's example, we are continuing to use the sashelp.cars dataset. The sashelp.cars dataset has a total of 10 numeric variables in it. I'm choosing to list 8 of them here because I am just going to go ahead and ignore invoice and MSRP because I'm interested in modeling MPG highway, and those aren't going to have an influence on MPG highway. We begin by looking at our scatter plot matrix. And I've listed MPG highway first in my variable list so that the scatter plots for that are on the top row of my matrix. I'm looking to see where my scatter plots appear linear. Now it's difficult to tell for some of these, especially in this first one where MPG is compared against cylinders because cylinders is a discrete variable. The next couple look like they could possibly be curvilinear. I'm not sure. We get to the 5th one, and that actually does appear to be linear. And we'll scroll down and we'll see that that variable is MPG city. And it does make sense that MPG highway and MPG city would be highly correlated with each other. In fact, let's take a look at correlation coefficients in ProcCore. I've got my same variable list. I'm continuing to keep MPG highway at the top of the list. And I will look now across that top row at my correlation coefficients, and I'm looking for the highest one. I'm going to ignore the 1 because I know that any variable will be perfectly correlated with itself. That's not what I'm interested in. I see across these values the highest one is 0.94 for MPG city. The next highest is weight, negative 0.79. It is okay that it is negative. The negative just indicates that it's an inverse relationship rather than a direct relationship. And then the next highest would be engine size. If you find it difficult, as I do, to read across an unordered list, you can have SAS spit out those values in a rank order, and you can tell SAS how many to list. So let me run this piece of code with the best equals option. I'll scroll to the MPG highway row and I see those correlation coefficients are listed in order of their absolute value. So MPG city is the most highly correlated according to our coefficients here, then weight, then engine size, then cylinders. All right, now we'll move on to our regression model. And notice that I have purposely listed my variables one at a time on the lines of code here so that I can comment them out as I'm eliminating them. I've also added the VIF option. Again, that's for variance inflation factor. Let's run this piece of code. In my results, I will first look at VIF. And I see some of the values are greater than 5. I'll find the highest value, which is 8.37, and eliminate that variable. So I will go back to my code and I will comment out engine size and then rerun my regression step. Looking at VIF again, I still have some values greater than 5. The largest one is for wheelbase. So I will eliminate wheelbase from my analysis. Now all of my VIFs are less than 5. It's time to turn my attention to significance. I want all my variables to be significant at the 0.05 level. And 4 of them are, but cylinders is not. So I will now eliminate the cylinders variable. And that should give me my final model. But I do not want to ignore some certain overall metrics, including my p-value, that is significant. My r-squared is high. My adjusted r-square is close in value to my r-squared. That's good. We don't want these to be drastically different from each other. And just to double check, all my VIFs are less than 5 and all of my variables are significant at the 0.05 level. All right, great. So I've got my final list of predictors: horsepower, length, MPG city, and weight. And now it's time to write my equation. And it would be helpful if those estimates were in a data set, and I can send them to a data set with my outest equals option. So I will run this step now. And I'll take a look at that data table. And in it, I should see those values that were in my parameter estimates table. All right, now in the PowerPoint, I went over 3 methods for writing your equation and making predictions. One was by hand, which I said was not recommended. That was just to show you how it all works, but that introduces the possibility of transcription error. Then there's the method of using macro variables. I've shown this to you before with simple linear regression. It's just now we've got some extra betas here. And I'm going to assume that you can continue that on your own and move on now to talking about residuals and then the scoring option. So you would take those macro variables and write your equation, but you have some extra terms here. Like we saw last week when I introduced simple linear regression, we can continue to add terms for additional variables. And now I've got this extra line of code here in line 99, and that's calculating a residual. That's the difference between the actual value for MPG highway and our estimated value that we're getting with our y-hat equation. And we would like for those residuals to be small. And we could use a proc print step and inspect those where we print out our estimated and our residuals and see. But let's move on now to proc score because that's something that's new here. Proc score will do all of our calculations for us without our ever having to write the equation. Now we've got 3 things to talk about here in line 114, score equals. That tells SAS which data set has our estimates in it. The out equals tells SAS where to write our modeled values or estimated values to. So this estimates were the parameter estimates from MultliReg. These estimates are estimated values from our model. And then this type equals just tells SAS that we're doing this from MultliReg. And I've got my 4 predictors in my variable list in proc score. Now I'll run this and then show you that y-hats data set. It has this variable called model1. If I scroll all the way to the right, these are my estimated values for MPG highway for each observation. And if it's helpful to you, instead of using model 1, we can call that y-hat because these are the same. And then my residual, again, is just the difference between my actual MPG highway and that estimated value. And we can print out some observations and inspect those residuals and make sure that they are on the small side. So for the first 5 observations in our data set, we have the actual MPG highway. We have what our model or our equation estimates the MPG highway to be, and then we have the difference between those, and these values do look rather small. So I would say that this is probably a good model. And that concludes my video on multiple linear regression part 1. Next week, we'll look at partitioning data and error metrics.